Hi, everybody. Welcome back to Environmental Organic Chemistry with Dr. Lisa. So we're continuing the Introduction to Thermodynamics lecture, and I'm sorry, but this is where I have to get into some heavy, fun stuff. So I'm gonna show you like chemical equations and stuff now, which I know you hate, but trust me, it'll be okay. We'll get through it together. So why do we care about thermodynamics? Well, thermodynamics is equilibrium. It's determining where a chemical will ultimately end up. If we wait until the end of time, where is it going to go? So in the environment, chemicals can be transported long distances if they're in the atmosphere, for example, or if they're in the water column. Sometimes if they're in a flowing river, they can be transported over long distances. But if they are in things like the solid phase, like sorbed sediments, then they won't go much of anywhere. So in the upper Hudson River, General Electric was using PCBs and they were discharging them into the river. And PCBs are not very soluble. If they had been, they would have all just floated away and we wouldn't have to worry about it. But they're not. They're not very soluble, so they stuck to the sediment, and the sediment doesn't move much. And so here we are, 50 years later, still worried about the PCBs that General Electric discharged into the Hudson River. Another example here is Freon 12. Freon 12, Freon 12 here, CCl2F2. Yeah, this thing, can undergo reductive dehalogenation reactions, but those things only happen in reducing environments, like environments where there is no oxygen. So that would be like at the bottom of sediments in a lake, or in a sewer, like at the bottom of sewer sediments, where there's a lot of methane being produced. That's why sewers occasionally explode. But the problem is this Freon 12 has a very high vapor pressure, so it just volatilizes away. It doesn't stay in those environments, so it can't undergo that reaction. So that's why it's important to understand thermodynamically, eventually, where does the chemical want to end up, because it'll have an important impact on the chemical's fate. So thermodynamics quantifies a compound's affinity for the environmental compartments which are available to it, and implies how much energy you need to input into the system to move the chemical. Sometimes the chemical will say, like, I will go into the gas phase, but it's going to cost you, right? Or it'll say, screw it, you're not giving me enough to force me to go into the gas phase. I'm just going to stay here in the sediment. So understanding the amount of energy it takes to move chemicals from one phase to another is very important. Notice that this is not telling us anything about kinetics. We're all just totally dealing with thermodynamics here. Now, frequently in this class, I'm going to anthropomorphize. Ooh, big word. I'm going to anthropomorphize, which means I'm going to talk about chemicals as though they are people, as though they have desires and feelings. Of course, we know that they don't. So when I say a chemical doesn't want to vaporize into the gas phase, what I really mean is that it has a low vapor pressure and it takes a lot of energy to vaporize the chemical. But it's so much more fun to talk about chemicals as though they're people, right? So that's why I do it. All right, so equilibrium is related to kinetics. Now, you may have seen this example before. So here's an example for we have little chemical A moving over to chemical B. It could be some transformation. It could be absorption reaction where A is the gas phase and B is, the surface of a leaf, something like that. And it's reversible. So there's a forward rate constant and a backward rate constant. So the rate law for the disappearance of A is minus dA dt is equal to K1. That's the rate at which A is disappearing times the concentration of A, minus K minus 1 times B. That's the rate at which A is appearing or being reformed. And it just so happens that if you switch the sign, that's also to equal to dB dt. And at equilibrium, there's no change in concentration. So dB dt and dA dt are both equal to 0. Goose egg, right? And so mathematically, right, if we move this over to the other side of the equal sign, K1 times A is equal to K minus 1 times B. And at equilibrium, that's where the products over the reactants, that's the reaction quotient. At equilibrium, that is where that ratio stays constant. So B over A is constant, and that tells us that K1 over K minus 1 must also be constant and equal to the equilibrium constant. So, woohoo, look, equilibrium concentrations are directly related to the rate constants. Right? Mind blown. Very exciting stuff. Okay. And also, sometimes the kinetic expressions for things like air-water exchange include within them thermodynamic numbers. So we need to understand thermodynamics. And sometimes you can relate equilibrium to kinetics via things like linear free energy relationships, which we'll talk about later. Okay, so your textbook uses this thing mu, little baby mu here, to talk about the, if I can get my pointer working again, here's mu, to represent the chemical potential of a chemical, right? So it's the energy status of a molecule in a system. So for example, benzene in water. And it incorporates all of the internal energies, which is the chemical bonds of the benzene itself, the way the benzene would vibrate or flex or rotate. And it also includes all the external energies, which is like how the molecule interacts with its surroundings, interactions with surroundings, and also the whole molecule transitions, which for benzene, there's not very many because it just kind of, it's so symmetrical, it's totally rigid. But like, let's say it was hexane where it can bend and flex and have different conformations and stuff. Then this would include things like whole molecule transitions, orientations, etc. I just gave the example of the cyclohexane with the chair and the boat formations. And so those would include that kind of transitioning from boat to chair would it be included here under transitions and orientations. So energy status is a function of, not surprisingly, temperature, pressure, chemical composition, right? So, useful tip, if anyone ever asks you, what does this depend on? And you say temperature, you're almost always right. So if you don't know what to say, just say temperature. And you can think of this mu, our baby mu here, as being the average energy per molecule. Average energy of mu, average energy for each benzene molecule. So if we wanted to write that in fancy math, we would say that the free energy G, and the parentheses here is a function of pressure, temperature, N is number of moles, and I is the chemical you're interested in this case benzene. And that is equal to the sum of all the chemical potentials of all the individual molecules of benzene, all added up for every single molecule of benzene. So the chemical potential is thought of as the free energy added to the system every time you add a little increment of I, which in this case, again, is benzene. Every time you add a molecule of benzene, how much are you changing the chemical potential? Well, that's your dG over dN, number of molecules, the change in free energy for the change in molecules. And keep in mind that this is a function not only, remember I was talking about how the notation in the textbook is difficult? I is your chemical. J is all the other chemicals that might be present in the system. And they are also important in determining the free energy of your baby chemical I. And by definition, this 3 equal sign thing here means by definition, chemical potential mu is equal to G, what we think of as delta G, or free energy, which we know is equal to H minus T delta S, right? Hopefully that's familiar to you from, like Chemistry 101. All right, so in the real world, if you have two populations of a chemical, so for example, the chemical is here's a really stupid example of two flasks, right? They're joined together by this stopcock, and one of them has liquid benzene over here, which means there's a lot of benzene molecules, and one of them over here only has some gaseous benzene, which means there's not very much benzene over here. Right now, they're not at equilibrium. So that means that the chemical potential over here on the left, mu1, is not equal to the chemical potential on the right, mu2. In this particular case, mu1 is greater than mu2. So if you open the stopcock, what's going to happen? Well, benzene is going to move from a high concentration to a low concentration. The net movement of benzene, there'll be benzene going both directions, right? But the net movement is to have benzene going this way. And that will cause mu1 to decrease and mu2 to increase. So it'll be driving against this gradient until you get to a point where they're equal. And then there will still be movement back and forth, but there will be no net movement. For every molecule of benzene that moves to the right, there'll be one that moves to the left, and they'll cancel each other out. So the problem is this thing mu is great and everything, but there's absolutely no way to measure it, right? So I'm not really sure what the point is. You can only determine the differences in mu, which one has a greater mu. So like in this system, I can definitely tell you that mu1 is greater than mu2, but I can't tell you the absolute value of mu1 or mu2. And the way you determine those differences is based on the tendency of the chemical to move from one situation to another. If it's moving in one direction, then you know that it must be moving toward the area where it has lower chemical potential. So we need a reference point, right? We need some place to use as our reference point. And so frequently we use the gas phase or also sometimes the liquid phase as our reference point, the pure gas phase and the pure liquid phase. And why do we do that? Well, because they have ideal behavior. You can assume ideal behavior in the gas phase because of the ideal gas law, and you can assume ideal behavior in a pure liquid because it's pure. It's sort of by definition, it's ideal. So in the next slide, we're going to talk a little bit about the concept of fugacity.